I'm Tim Ventura from AmericanAntigravity.com, and this is a follow-up interview with Dr. Eugene Podkletnov, world-famous Russian physicist and chemist known for his work into gravitational waves and gravity beam generation. During our previous interview, Dr. Podkletnov told us that he'd been able to generate hundreds of pounds of force in beams of pure gravitational energy, and we're conducting a follow-up interview to learn a little bit more about the details of his experiment. Dr. Podkletnov, can you hear me okay?
I read you perfectly.
One of the responses that we had online was, with nearly a decade of experience, why haven't we been able to see video or photos of your experiments up until now?
Well, first of all, when I began those experiments in Finland, in Tampere, it's not a habit here in Finland to make any videos or photos of the equipment or of the experiment. It's typical for the United States, but here in Europe it's a bit different. And the same thing goes for Russia, especially with the last experiment in the Moscow Chemical Research Center, because the whole center is a very complicated structure, and some of the works are closed for wide public. They're not secret, but they're simply dangerous because we use high voltage, several million volts, so they're closed. And well, we have special signs on the walls of the laboratory which do not allow to make any photos. It's the policy which is accepted at this scientific center. So I didn't want to change the rules.
Oh, absolutely. Well, in light of the publicity that you've had recently, have you given thought to doing any photos or video in the near future?
I think I will try to make something. I discussed this possibility with the administration. They think it might be possible, but at present we have no videos and no photos at all.
Oh, okay. Well, I look forward to hopefully receiving some in the future, if it turns out that it is possible. Well, to move along, have you been able to obtain funding from government or private interests? Has there been a fair amount of interest that's come forward and tried to provide some funding for your experiments?
There is a certain interest from several circuits, but it's private sector mainly, because governmental policy towards all the research in the field of gravity and experimental gravity is it's not a popular trend, so we don't get much money from the government. Of course, we use the ready installations at the technological center, but there is some interest in general all over the world and in the United States, in Great Britain, but we didn't get any funding from the government. We get rather small funding from private sector, as I mentioned, but our plans are really amazing, and we need considerable funding. So this topic, gravity, is first of all, it is a bit unusual, and we need some exotic material, we need special installations, we need cryogenic systems, also we need the help of people who are top qualified in their own areas, and this all costs a lot.
Yeah, definitely. Well, with the actual testing, one of the questions that had occurred to me when I sat down and took a little bit of time was, as these are presumed to be gravity beams, have you noticed any time effects?
It's difficult to say, because it's not practically a gravity beam, it's a gravity impulse, so it's very short in time. And because of these limitations, as it is short in time, we didn't notice any time effects and didn't even try to measure. Maybe they are present. They are definitely present when we are working with the rotating disks, definitely. And we had some experience with this, but with gravity impulse generator, we simply didn't organize any measurements.
Absolutely, that makes perfect sense. Well, I was wondering, on a personal note, you'd mentioned that this was over hundreds of pounds of force for a very short period of time, and I'd wondered, has this been able to punch holes through lightweight substances, or Is it more of just kind of a motion on them?
It all depends on the voltage that we apply and also on the structure of the superconducting emitter. So at the maximum possibility of our materials at present, we can obtain rather big impulses, so they are able to deform metal plates with a thickness of a couple of inches, and they are able to make holes in concrete walls. So we are not speaking about some lightweight substances, but concrete wall is something very solid.
Oh.
And they deform metal in the way that a hydraulic press might do it, but the impulse is very short in time. So of course we can build a system and use several Mach generators, so we can give a series of impulses that will definitely improve the situation. But at present we can treat different materials with our gravity impulse generator, and also what is important that we can hit different objects at big distances.
Absolutely. Well, you know, in terms of putting holes through concrete, it makes sense that the holes would remain, but with metals, after the metal is deformed, do they snap back after the beam is gone, or do they remain deformed?
No, they just remain deformed. It's just like very like a punch, very short in time. So it's an close to an explosion action, something like this.
Oh, okay, okay. I'm planning on buying a small superconductor and testing some myself. Hopefully, I don't have a 5 million volt system. I think 5,000 with a very high amperage. So hopefully, I doubt that it would do metals, but I've thought maybe paper might be something to experiment with and see if I can.
Well, I think it's possible.
Oh, okay. Well, I'll definitely have to move forward with that. Well, one of the things I was wondering about was whether you've been able to do efficiency calculations for the force beam.
Well, Giovanni Modenese calculated made some preliminary measurements and gave the forces in joules, but we practically did not try to calculate. We wanted to simply to see the results and how the different objects react to the action of this impulse. So we didn't make any precise calculations.
Oh, okay. You'd mentioned in the past that this tends to defy conventional relativity theory. I was wondering if you might have any specific examples of things that caught your eye as maybe being not right or outside of what the theory predicts.
Well, first of all, I didn't say that our experiments defy conventional relativity theory. No, they don't. But if we speak about the experiment with the rotating disks, I simply mentioned that we're rotating metal or superconducting objects at very high speed, and as this rotation around its own axis is not it's an absolute rotation, so it's absolute movement. It's not relative. That's why the relativity theory is not applicable to our rotating disks, because it's entirely a different thing.
Oh, okay. So it just doesn't apply, but it doesn't invalidate it at all.
No.
I should apologize for getting that one incorrect. Oh, does the inertia change in proportion to changes in mass? The reason that I kind of wrote that down was really in relation to Fran Diakino's research, and he believes that these aren't equal, that they just tend to appear equal to us in our frame of reference. But I was... Oh, I'm sorry.
Well, according to our understanding and our experience, we did not make any difference between gravitational and inertial mass, so we think that they are equal. also in case with the impulses are too short in time to notice any difference. And we didn't make any special experiments just to distinguish gravitational and inertial mass.
Oh, okay. Oh, in terms of the actual emitter, the superconductor, I'd read the experimental write-up. I believe it was 47 millimeters, if I remember correctly. But I was wondering if changing the size or shape affects the beam output. Maybe makes it stronger or refocuses it, perhaps?
Well, if we speak about the size of the superconductor, there are some limitations. The diameter of the superconductor shouldn't be smaller than 4 inches because of the Schwarzschild's radius. And if we speak about the shape, well, the superconductor can in fact have different shapes, and the impulse will repeat the projection of a certain shape. So it is important.
Oh, okay. Well, that may rule out my experiment. The largest I've seen online, I think, is a 1-inch superconductor, in the United States at least, so I'm not sure if they sell 4-inch ones, although if they did, it would be worth the money.
Well, it's very important. We didn't get any good results with smaller superconductors, and also it's much more difficult to get a flat discharge with the superconductors that are small in diameter.
Oh, okay. Well, have you noticed any changes in the molecular structure or maybe compression for the targets that you've sent the beam through? Like you'd mentioned, metals deforming and holes through concrete.
Yeah, we did not see any compression effects or any change of the molecular structure. It remains the same as it was.
Oh, okay. So it's just a large-scale deformation from force, but not anything internal then?
No, nothing internal.
Oh, I should ask if the beam loses energy as it penetrates materials. Does it naturally decrease with distance?
Well, that's an interesting question, and to our great surprise, and we made a lot of discharges, so the installation was working for about 4 years now. The beam practically does not lose energy when it meets the materials. It can pass through the brick wall or concrete or metal plates, very thick ones, and plastic materials also. It seems that it doesn't lose energy at all, which seems a bit strange, but we don't want to break any laws, and simply the system where we are working, it's not a closed one. Therefore, the second law of thermodynamics is again not applicable here. And if we speak about the action with the distance, the dependence of the energy on the distance, we don't have much experimental data, but what we have now is first measurement at the distance of 1.2 kilometers, and there is no loss of energy. And the latest experiments, the distance was 5 kilometers, and the beam penetrated through several houses, which were made of concrete. So we did not measure any loss of energy, but according to some calculations and the evaluations that we made, with a distance of more than 100 kilometers, we should get some decrease of the energy. So this work awaits us in the future.
Oh, okay. You'd mentioned 5 kilometers. Did you notice any change in the focus of the beam? Did it widen or perhaps get smaller as it travels?
If the main solenoid, which is wound around the chamber, is made in a good way, then we have a very good discharge, and practically it it contains the same form as it was. But with a distance of 5 kilometers, we noticed that there is the beam is not so focused. It goes a bit wider than it was. So there are some deviations in the shape of the impulse. It becomes a bit wider.
Oh, okay. I collected a few questions online, and one person had written me, is it possible to generate more work along the path of the beam than energy put into the beam? I think they were asking about potential over unity applications. But
it's surprising that the energy that we put inside the discharge it's much less than the energy which the impulse produces, and the work that it can make is bigger than the energy that we put inside the beam. But that doesn't mean it's an over-unity device. Simply we create the conditions when the interactions of magnetic field and electric field and special behavior of the Bose-Einstein condensate. So with all these parameters, we provide the interaction of the fields and of the material with the subatomic particles. We may call it zero-point energy or whatever it is, or ether. But anyway, when normal matter interacts with subatomic particles, special energy is obtained, and we can use this energy. So our installation is like a key which opens the energy of the subatomic particles. This is at least our explanation.
Sure. Well, and it sounds like it is kind of opening up, perhaps in some ways, more energy than is immediately available.
Yeah, that's right. Also, we are not speaking about any closed system. This system is an open one, and we don't break any laws from our point of view.
Oh, okay. Well, you had mentioned that you're actually working on some publications, and I guess in some ways that kind of ruins my next question that I've collected online. They'd asked if you're going to publish more in the near future.
Of course, the interest to this problem is growing in all the countries. We got a very interesting offer from China. They have a special project at the University of Beijing, and there is a certain interest from the private sector in the United States. So as soon as we get the funding, we will try to organize all these experiments in a more detailed way. But at present, what is extremely interesting that we measured, or we tried to measure the interaction of this beam with the light, and some preliminary results were published last year in the Journal of Low Temperature Physics. It was in August. It's my article with Giovanni Modanese. And we continue this work now, and also we tried to measure the speed, the propagation speed of the impulse. And we are very cautious about it because we don't want to frighten the scientific community, and also we want to be absolutely sure that the results were checked and rechecked several tens of times. But it seems that based on what we have now, and we already were working for a year and a half on this, the speed of the impulse is much higher than the speed of light. And with the parameters that we use now, with the present emitters and the voltage of 3 and 5 million volts, the speed is about 63-64 C, which means that the propagation speed of the impulse is close to, it is practically 64 times faster than the speed of light. But we would like, of course, to measure all these parameters using different measurement systems, different approaches. At present we used two-atomic clock, and we think that our experiments were precise enough. But we would welcome, of course, the advice of the international community and the advice on how to measure the speed of the impulse in a very precise way. As soon as we get good confirmation of the results, we will try to publish all this information.
Oh, okay. So there's definitely more coming along. You know, one thing that I found helps with the lifter experiments and others that I've conducted, and again, if you once you reach the point of taking film, I found that film analysis helps a lot, at least for my experiments. And one of my favorites has been working with smoke and cloud chambers. And, by stopping the tape and rewinding, I found that I can find a lot of little things going on that I never noticed at the time I filmed it. So, perhaps that may be something that'll be valuable if you're able to bring a camera in and get some photos.
Yes, that's a very good approach. We'll take it into consideration, of course.
Well, I was wondering, you'd mentioned that there's interest from the private sector in the United States and from China, but do you know if there are any duplication efforts or replications underway by other groups for your research?
I know that there was a big interest in Boeing, but I don't know their secrets. And I know that the Department of Defense in the United States is also interested in this program, and that's why they invited Dr. Ning Li to lead their scientific laboratory. But at present I don't know any official replication of my gravity experiments, mainly because they are hard to organize, they are rather costly, and the official attitude of the, let's say, politically correct science to this problem is negative, so it creates a lot of difficulties. But I don't hide anything, and if people contact me directly or by email, I usually try to give all the advice that I have and to share all the experience, because the problem is too complicated for one country or for one lab to succeed, and the gravity should be studied all over the world using the best forces and the brains of different scientists. That's the key to success.
Absolutely. Well, and I've always had great success in terms of contacting you, and you've always been incredibly helpful with my questions, and so I'm sure others will have a similar experience. But one of the obstacles to independent replications, it sounds like, is the 4-inch superconductor. Do you know if those are manufactured and sold anywhere, or is it a process that everyone has to go through to build their own?
Frankly speaking, it's a part of my know-how, but if we speak about extremely effective emitters, but normal emitters which allow simply to measure small effects, it's not a problem, and I think that American superconductor can help easily to make the emitters of this kind. Or also there is a nice firm called Superconductive Components in Ohio, Columbus in the United States, and they are more or less familiar with my technology, and they can, I think, make their good contribution to this.
Oh, okay. So essentially, by using a smaller superconductor, you have a smaller effect, but that can be tested using more sensitive equipment.
Still, the diameter of the disc should be not less than 4 inches. No, I speak about the structure. The structure for very efficient emitters is a bit difficult, and it takes a lot of experience to achieve this structure. So even if I give the detailed description, it's a bit difficult to make it without my help. But with normal emitters, which allow you to push a thick book away from the table, it's possible to make it. It's not so complicated.
Oh, okay. Well, I had one other question about, this person was also asking about video, but they were also asking about a moving flat glow discharge. And this was something I thought might be in your notes, perhaps, that I'd missed when I read through them.
Well, in order to make the video for the flat glow discharge, we should use a high-speed video camera, which we don't have at present, so we just want to rely on our keen sight, but it's a bit difficult. We're planning to make it, but even with normal eye, when we have normal discharge, I mean a spark, as in Van de Graaff generator, or a flat glow discharge, which repeats the configuration of emitter, it's possible to see it with your own eyes. We don't need any camera for this.
Oh, okay. Well, just to wrap things up, because we're almost out of time, again, it sounds like you're getting amazing results. You're able to actually, put holes through concrete and bend metals with this at 5 million volts. These are remarkable results. Is there anything you'd like to say in close?
I don't think that these results are remarkable. In general, this subject called experimental gravity research, it has a very big potential, and if we compare how complicated this problem is to the problem of, let's say, nuclear explosion, I think that gravity research is much more complicated. But even if we speak about nuclear power, there was a period in the United States when everybody was interested, and military people wanted to make some researches, and the government was interested. And then people came and said, could you please make a small explosion, and then we will give you money for a big one. And it's impossible to make a small nuclear explosion somewhere under ventilation. The same thing refers to gravity. It's an enormous problem, and we can't get much if we don't have an organized approach as it was in the nuclear program, for example, in the United States. So only combining the knowledge of different fields, of different physicists and chemists and material scientists, theoretical physicists, only making them work together, we can make a breakthrough in this field, because it's a very, very serious research.
Absolutely. Well, thanks again for your time, and we definitely look forward to following up with you more in the future.
Thank you. You are welcome.